So for asphalt mixture, we need to put bitumen, to heat the bitumen, and to heat aggregate, and to mix both. So before presenting the result of asphalt mix test, I just want to come back to some basics of pavement design. Asphalt pavement is a multi-layer structure. We have the surface layer. It is the surface we can see when we look at on a road. And under this surface layer, we have many layers. The first one is called a binder layer, and we have a base layer and sub-base layers. And the type of test we have to perform depends on the type of layer we want to build. So in this 2D, we choose to characterize materials, to design materials for binder and surface courses. And in French mixed design methodology, we have to perform several tests I present here. We have some very basic tests and some tests a little bit complicated, but sometimes necessary for pavement design. So I will just present you two results. The first one is the water sensitivity or water resistance or stripping test of asphalt mixture. It is the objective is to evaluate the effect of water on a pavement structure. As you know, when we build the pavement, it will subject to many climatic conditions, such as raining, the effect of water when it's rain. So I will evaluate the effect of water resistance of the mix we design. And I will also present an example of study we perform regarding the evaluation of the stiffness of the pavement. Yeah. And for the rotting or wheel track test, this still in perspective. So in order to prepare the specimen for the mechanical test, as I explained, we need to heat the aggregate and to put aggregate in a mixer and add the blend, the binder. So the binder here is a blend of bitumen, lignin, and waste cooking oil, and we mix them for 5 minutes. And we have many ways to compact specimen in laboratories. So here I choose to present only the giratory compactor that allows to prepare cylindrical specimen. And for the property of aggregate we use, I present here the most important one. It is the grading curve that give an overview of the size of aggregate we use for road application. So the higher diameter of the aggregate for road application here is approximately 10 millimeter, and the smallest one are approximately 0.063 millimeter. And this type of material is in French designation is called BBSG, as I have written here. And this type of pavement is used for binder and surface courses of the pavement. Well, the first test we perform is the water sensitivity test. So the principle is relatively easy to understand. We prepare cylindrical specimens and we put them in water for 3 days at 40 degrees, and we put some reference specimen in a climatic chamber without water, but at the same temperature with others for the same duration. And after 3 days, we perform a compression test. It's exactly an indirect tensile strength test. So here you can see the specimen and the principle of the test that allow to determine the maximum force. So when we perform the test, we can record the data like this. We can have a representation of the force versus the time of the displacement, and the most important parameter is the maximum force. And for specimen kept in water, we divide this result by the result of the maximum force or the maximum compression strength of specimen cured in air. So we have a set of sample kept in water and a set of specimen cured in air, but at the same temperature. And as you can imagine, if this ratio is small, this means that the water have a higher effect on the specimen compared to specimen that are kept in air. So when we want to to produce material for road application, we we try to find the good combination of aggregate and binder so that this ratio is higher as possible. Sorry. So here I present the result of the indirect tensile strength. For example, here I add also a reference concrete made with only bitumen, and you can see here some example of results. When I wrote here ACB 20L3H, it means that asphalt concrete containing bitumen with 20% of lignin and 3% of HIU, which is a type of waste cooking oil. And you can see that when this color represents the specimen, the ETS of the specimen uh, put in water for 3 days, and this one represent the ETS of the specimen uh, kept in air for the same duration. And we can divide, for example, this result by this one, and to obtain a ETS ratio, which is represent in the right side of the slide. So as you can see, for the reference concrete uh, produced by using only bitumen, we have a higher ETS ratio, and for specimen produced with biobased binder, we have slight, we have a reduction of the ETS ratio. And normally, when we want to choose material for road application, um, we are looking for material that the ratio is over 0.7, which means 70% of ETS ratio. So I can conclude that even if the ETS ratio decrease when we use biobender, the obtained value is still higher than the required specimen, the requirement for water sensitivity value, which is 70%. So the second test is a test that allow to determine the stiffness of asphalt concrete specimen in laboratory. We have there is a lot of tests, standardized tests that allow to determine the stiffness. Here I choose to present the one we have in our labs. The principle of the test is to submit a prismatic specimen. Here in the right side, you have some example of prismatic specimen of asphalt concrete. And we perform the test at several temperatures. As you know, in winter and in summer, the road is subject to many temperature variations. So we perform the test at several temperature. So this design is in a climatic chamber, and we can change the temperature of a climatic chamber. And we perform the test at each temperature. So the principle of the test is to apply a sinusoidal loading and to determine the displacement and the force we need to move the specimen. And by determining the force and the displacement, we can calculate the stiffness modulus of a specimen. So here I present the results, the final result of a stiffness. We call it E star, and on the right part of this curve, the right part represents the stiffness at low temperature and higher frequency, and the left part represent the result obtained at high temperature. As you know, when we hit asphalt face specimen, it can become too softer, and when we decrease the temperature, it's become too hard. So this representation allow to combine all the results in the same picture. It was also possible to present the result we call isothermals, which is the stiffness at each temperature. But this representation that we technically call master curve allow to have a big picture of how the stiffness increase and decrease depending on the temperature. So I can also precise that the gray curve represents the stiffness modulus of the reference asphalt, and the orange and the green one represent the data for the bio-base bender mixture. So when we look at the evolution of stiffness resistance, stiffness modulus, we can say that the mixture we design using bio-based bender still have a stiffness comparable to standard uh, bitumen mixture. So those are the two results I want to show you, and I will finish the presentation by thanking thanking everyone for attending this webinar, and for also thank European Union for founding this project, and also thanking all partners involved in this project. So, so thank you, everyone.